So now let's look at the second theorem about the uniformly converging sequence of the integrable functions. Okay, so this is the theorem. It says, suppose f sub n is a sequence of integrable functions on the closed interval from a to b, and f sub n is convergent uniformly to the function f on this interval ab. Then the limit function f is integrable on ab, and the limit of the integral from a to b of the function f sub n is equal to the integral from a to b of f. So this theorem tells you that if you have a integrable sequence of integrable functions, then it uniformly converges to a function. That function must be also integrable, and you can actually interchange the limit sign and the integral sign to get this result, right? And you have this kind of result for the pointwise convergence, because the pointwise convergence we have some examples that says they may not be the same, right? The limit 1 is 1. I remember the example that the integral is 1, then the limit is 1, but the limit function, you take the integral, which would be 0, right? So they may not be the same. So let's look at how to prove this theorem. So the first thing, we want to prove this function is integrable. So we know that a function is integrable. It's equivalent to see that the upper integral equals the lower integral. Okay, so how to prove the upper integral equals the lower integral? That we just need to show that for any epsilon greater than 0, then the difference between the upper integral and the lower integral is less than epsilon, because epsilon is arbitrarily small, right? Greater than 0, so there's no other choice. So this difference must be 0, right? So that means they are the same thing. So then we can prove this function is integrable. So now we will take arbitrary epsilon greater than 0, right? So since this f sub n is uniformly convergent to the function f on ab, then this is the definition for the uniformly convergence. That means that for any epsilon greater than 0, there exists a capital N greater than 0, then f sub n minus f is less than epsilon for all n greater than or equal to the capital N and all the x in the domain AB. Okay, then let's rewrite this inequality as this form. Okay, as this form. We can write this inequality as a compound inequality. Okay. Okay, with this inequality, let's take the upper integral for the right side. Okay, for this inequality, let's take the upper integral. Then you will have this one, right? You will have this one. We'll take the integral, upper integral. And then it's equal to the integral of AB. The reason is this f sub n is integrable, and epsilon is also integral. It's a constant, right? So it can be written that the upper integral is equal to the integral, right? So let's compute this one. This will give you that this result, right? This is the integral of f sub n, and the integral epsilon equals b minus a times epsilon. The b minus a is positive because b is greater than a, right? And similarly, we can take the lower integral for the other part of the compound inequality. So now actually we take the lower integral for this on both sides for this inequality. Okay, then you will get the lower integral of f is greater than or equal to the lower integral from a to b of f sub n minus epsilon, right? Is equal to, because the same reason is this is integrable, this is integrable, so the lower integral is equal to the integral, right? Then we do the calculation for this integral, it will be this one, the same thing, right? Then let's take the difference between this, the upper integral and the lower integral. Okay, let's take the difference. Okay, we know the upper integral is always greater than the lower integral, right? By the definition, right, using the double sum. So the absolute value is equal to the difference between the upper integral minus the lower integral, right? And then we plug in, right? We plug in this result and this result here. Then we have the less than equal to, right? Less than equal to, this one is less than equal to this one minus a bigger one, so it's smaller than, right? Smaller than equal to. So you will have this one. And then we simplify, right? This and this cancel out, and this one minus the negative one, which would be 2b minus a times epsilon. And this is a constant, so it's less than equal to a constant times epsilon, since epsilon is arbitrary. So we can say this one, this must be equal to that. The upper integral is equal to the lower integral, so this function f is integrable. Okay, so now we want to prove the limit, right? So we consider the same epsilon and consider the same capital N. For the n greater than or equal to the capital N, and we want to show this one is less than epsilon, so that means the limit of this part is equal to this part, right? This integral. Okay, so this is the definition of the limit. So now let's do the calculation. Okay, so this is the we combine together, you will have f sub n minus f. Then we use the inequality we have learned for the integral, right? You can put the integral inside, but you will enlarge this inequalities, okay? You will have the less than equal to. And for this one, this is the, we know, sorry, here should be f, not f sub n. And we know because the uniform convergence f sub n minus f is always less than epsilon, so you will have this one less than equal to the integral of ab of epsilon. So it's equal to b minus a times epsilon. B minus a is a constant, right? Because ab are given. So this is the less than some constant times epsilon. So that means this would be small enough when the lowercase n is greater than or equal to the capital N. So that means by the definition of the limit, right? This means the limit of the integral from a to b of fn equals the integral of ab of f.